Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about cascaded op amps, and we're going to do two examples where a cascaded op amp or cascaded connection is a head-to-tail arrangement of two or more op amp circuits such that the output of one is the input of the next. So for example, as you see here, the output of this op amp, let's say A1, is the input to this A2 operational amplifier. In the first example, we're tasked with finding VO, so the output of this op amp, and IO, so the current through this 4K ohm resistor. And in the second example, we're simply asked to find VO. If you want to pause the video and see if you can solve these and then come back to the video and see if you got the correct answer, please feel free to do so. So without further ado, I'm going to start with this first example. So for the first example, it's relatively simple. We have to realize that this A1 amplifier is a buffer. All right. And I have made a video on buffer circuits in the past, so please feel free to check that out. And the second example is a non-inverting amplifier. Again, it's non-inverting because of this plus here. Okay. So my output here is going to be, if you give me a positive, I'm going to give you a positive. If you give me a negative voltage, I'm going to give you a negative voltage. All right. And my ground is connected to the negative terminal. Okay. So I've done this in the past, but I'm going to go ahead and derive this again. But if you give me a non-inverting amplifier, this is Vin and this is V out plus minus. I know that in an ideal op amp, the input resistance here, let me call this Rn, is extremely high. Call that infinity. As a result, the current going into my positive terminal is 0. All right. Long story short, this node here is Vi. As a result, this node here is also Vi. So if you can see, this is kind of like a voltage divider circuit where if I redraw this, I could say that this is Vi, this is V out. And this Vi, if I call this, so again, this is R2 and this is R1. If I call this R2 and R1, Vi is going to be equals to R1 over R1 plus R2. That's just the voltage divider equation times V out. Since I'm trying to solve for V out, this is going to be V out is going to be R1 plus R2 over R1 times Vi. And then this is the equation you normally see, which is this 1 plus R2 over R1 times Vi. Okay. So that's for a non-inverting amplifier. All right. So this is my equation here. Okay, so what happens to this circuit here, A1? We set that for an ID op amp. If my voltage here is 8 volts, that means that my voltage here is 8 volts. That means that my voltage here is also 8 volts. So it's just a buffer circuit, all right? And I've made a video on that, so please feel free to check that out. I'm not going to dive too much into what the benefits of a buffer circuit is, but just understand that the voltage here is 8 volts. All right. So my Vn is equals to 8 volts. All right. R2 is equals to 8K ohms and R1 is equals to 4K ohms. As a result, VO is simply equals to 1 plus R2 is 8K divided by 4K times 8 volts. As a result, this is equals to 1 plus 2 times 8 volts, which is simply 24 volts is equals to V output. All right. And for my current, the current is pretty simple. IO is simply, we know that this 8 volts is here. So this is 8 volts. This is also 8 volts, right? So this node here is 8 volts. So IO is simply equals to 8 minus 0, so 8 volts minus ground, divided by 4K. So this is simply 2 milliamps. So that's your answer for IO. Okay, so if this made sense, please let me know down in the comment section below if you have any questions, and I'll be sure to get back to you. So let's go ahead and do the second example now. So again, go ahead and pause the video and see if you can solve for this. This one's a little bit more complex, but the idea is the same. So what I'm going to do is I'm going to label what my op amps are. So here I see that I have another buffer. All right. I see here this is an inverting amplifier. All right. The reason why is because I forgot to draw this here. This is connected to ground. All right, my voltage is going into my negative terminal. And then here we have another inverting amplifier. Okay, so what I'm going to do is I'm going to solve again for the inverting amplifier just as a refresher. But again, I have a video on this. So if I have a input resistance, a feedback resistance, this is V in, and this is connected to ground. What I'm going to say is that the current going in here is equals to the current going out here, correct? Simply because, again, since this is 0 volts, this has to be 0 volts. So all my current has to flow in this direction. Okay, and this is VO. So, right, you could write an equation, Kirchhoff currents law. If I call this I1 and I2, I1 has to equal to I2. All right, and I1 says VI minus 0 over RI has to equals to 0 minus V out over RF. If I go ahead and solve for VO, I'm going to get that if I multiply RF over RI, there's a negative here, times V out. All right. Oops, sorry. Times V in. So that's the equation for the inverting amplifier, just done quickly. So let me go ahead now and write out some things that I know. So since this is a buffer, this is 4 volts. This here is 4 volts. As a result, this here is also 4 volts. Okay. This here is an inverting amplifier. So I'm going to use, let me call this VB. All right. Let me call this VA. I'm going to say that VB is simply equals to minus my feedback resistance, which is 50K, over my input resistance, which is 10K, times 3 volts. So this is going to be 3 times 5 volts. 3 times 5, because 3 volts times 5, because the K ohms cancel out. So this becomes minus 15 volts. All right. So this VB here is minus 15 volts. All right. So the last part of this is we have to realize that since this is 0 volts, 0 ohms, 0 volts, this here is also 0 volts. And we can say then that the current going in through here and the current going in here has to equal the current going in here. So if I call this I1, let me call this I2, and let me call this call this I3. I can then say then that I1 plus I2 has to equal I3. All right, and I1 is simply minus 15 minus 0 over 30K. I2 is 4 volts minus 0 over 20K. Mistake here. Oh, yeah, 30K, yep. And this has to equal to 0 minus VO over 60K. Looks like I'm having some difficulties with my pen. But let's go ahead and just solve this all out. So VO is equals to minus 60K. And you have this to be 4 over 20K minus 15K over 30K. If I go ahead and I can multiply this here by 3 and 3. If I go ahead and multiply this by 2, this then becomes minus 60K times 12 over 60K minus 30K over, or 30 volts over 60K. That's 12 volts. Long story short, this cancels out. This becomes a plus, minus, plus. So then I get that VO is simply equals to minus 12 volts plus 30, which is equals to 18 volts. All right, so if you got this at the end, you got the right answer. If not, and you have any questions, please let me know down in the comment section below, and I'll be sure to get back to you. If you found the video helpful, please like the video, share the video, and subscribe to my YouTube channel. Thank you.